So
Okay.
let me just quickly welcome our next speaker for the short talk, Zubizarreta Casalengua. He's from the University of Wolverhampton in UK, and he'll be talking about modulating statistics of light. The floor is yours.
Okay. Thank you very much for the nice introduction. I also want to thank the organizers for giving me the chance to give this talk and for this wonderful week of very nice conferences. So I am working in my PhD right now in theoretical quantum optics in collaboration with Lopez Carreño, which is a postdoc researcher now, and I am under the supervision of Professor Losi and Dr. Del Valle. So let me first introduce what I mean with this term, this idea of statistics of light. So to quantify or to try to determine the properties of the quantum light, one thing that we need to do is to know how the photons are coming out the source of interest. So one thing what we can do is intensity interferometry, and the usual correlator, the usual average that we need to quantify or to calculate in case of being a theoretical physicist as me, is the G2 of tau. So the usual way to measure it is to have a Hamilton-Brown setup. We split the signal in two and measure the coincidences at one of the detectors. And then we calculate the correlation between them. So this is the coincidences between the photons that are separated by a certain time interval tau. Making the usual criterion is to take just the coincidences at the same time, and we usually use this U2 at 0 to quantify this or to classify the light. So the first possible value is to have an uncorrelated light, so the G2 is equal to 1. This is, for example, the case of the coherent emission coming from a laser, in which the photons come to the detectors uncorrelated to the rest. Another possibility is to have a bunched light. In this case, the G2 is greater than 1. A good example of it is the thermal emission coming from a bulb or coming from a black body. And the opposite case is to have anti-punch light. And this is a very important case because having a G2 less than 1 has no classical analogous and is a very quantum signature. And it's essential to determine if one source could be a candidate for single photon sources. So on the other hand, yep. Okay, sorry, I forgot that. To make a more in-depth classification, we need to take into account higher order correlators. So which is the probability to have more than 1, 3, 4 photons being detected at the same time. So now another important thing that I want to introduce before I go to the rest of my talk are the Gaussian states. So these are states that can be described by a Gaussian in the Wigner representation of the quantum light. So the first one, and I think it's very well known, is the thermal light. In this case, we have a pure mixed state in the sense that we only have diagonal terms in the density matrix, and in this case the G2 or all the Gn are greater than 1 and are equal to n factorial. Another well-known example is squeeze light. This is described by this complex number. R is the amplitude of the squeezing, and this is the phase of the squeezing. This is very well known and used because of the properties. They have reduced noise, so the noise is even below the vacuum noise in some instances, and is used in high sensitivity experiments such as LIGO that they used squeeze light to detect the gravitational waves. And it also characterized by having a G of n greater than 1. So this is bunch 2. And the last one is the displaced coherent state. This is the quantum description of a classical monochromatic wave. In other words, it's a way to describe the quantum state of a monochromatic light. So now we will forget about the thermal light because it's not very important its effect on what I'm going to talk later, and we will focus on what happens if I try to combine the squeezed and the displaced state. So a physical way to do this is to use a Homodyne scheme in which we mix through a beam splitter the light coming from the coherent state and the light coming from the squeezed state. We mix them, and then we want to analyze what happens with the mixed statistics. And just to say, the corresponding state, if we analyze it just by not as a physical system, but as just a mere quantum state, the resulting state is a displaced squeezed state. Just to remind you, if we analyze the light outcome in the coherent or the squeezed state, the G2, the resulting G2, will be always equal or greater than 1, so always bunch or coherent light. But if we mix them with the optimum phase match, we can modulate the light from being a bunch to being anti-bunch. And if we look at the region where the anti-bunching is stronger, we will notice that we need that the values for the coherent or squeezing amplitude should be very, very small. So this only works if the amplitudes, incoming amplitudes of the states are low enough. But now, if we take into account the rest of the correlators, G3, G4 in this way, defining this n norm, if you want to know more about it, you can you can read this reference. So if we look at the region where the G2 is stronger, we will find that it does not correspond to the region where this norm is less than 1, which is required to have a good single photon source. So what is happening here is that we are suppressing only the 2-photon contribution. So this is if we expand the G2 for this low amplitude region, in this low amplitude region, we will find that what we are doing is to suppressing the value of this P2, which is the probability of having 2 photons in the state. So now I want to make another mention to this Homodyne scheme, but in this case I want to separate the contributions between the incoming parts, right? So if I look at the mean field, so if I sum the outcoming mean field is just the sum of the mean field like in a classic wave. The amplitude is the total amplitude is just the sum of the amplitudes. Then the population or the intensity is the sum of the intensities plus another term that is coming from the interference of the mean fields. But in this case, the squeeze state has not any contribution in the mean field, so we just have a 0 there, which is innovative and has not a classical counterpart. If what happens if we decompose the 2-photon correlation, and we find that we have 4 terms. The first term is coming from the coherent state that always has a G2 equal to 1, and then we find three other contributions that we can separate like that. We have I0, which is related with the fluctuation statistics of the other source that is not the coherent state. This tells us if the state is bunch or anti-bunch prior to the mixing. Then we have I1, which is related to the anomalous moment. So if we have a non-Gaussian state in the one of the ports of the input ports, we will find that this I is zero. But in our case, both the squeezed and the incoherent and the coherent state are Gaussian. So this is zero for our case. And the other one, I think is the most important one in this case, is the quadrature squeezing term. This is telling us that the interference at the 2-photon level, if it's positive, so it will create a greater value for the P2 or a much smaller value for the G2. So we expect in this case to have a negative value for the I2. And if we write the conditions for the anti-bunching in terms of these contributions, what we find is that I0 should be close to 1, I1 should be close to 0, so it should be more or less Gaussian, at least to the 2-photon level. And we find that this I2 should be -2. And what is important is that in the next cases that we will see, these anti-bunching conditions are exactly the same. So this means that even if we are dealing with some dynamical systems, if we make a description just in terms of this kind of states, we will find that the outcoming light or state of light that it's coming from these sources can be described in this way. So the mechanism of having this anti-bunching will be exactly the same. So let me first introduce a easy example of this technique, applying this technique. And the first and the most simple case.
Zubizarreta? Hi, sorry, you have 5 minutes left.
5 minutes left. Okay.
That's right.
So yeah, I will skip this a little bit, but the idea is that we have a single photon emitter with dissipation. So we are studying an open quantum system. In this case, it is the most simple one. It's just a single photon emitter. We study the weak excitation ring because we need we need the amplitudes of the light to be low enough to use the description, and we will study the steady state region in all of the cases. Okay, so we do the same. We put the light coming from the single photon source here, and we put the coherent light here. And in this case, we have some contribution from the mean field, which is just the elastic scattering coming from this source, and the other part are the fluctuations because we are deleting we are deleting the mean field are the inelastic scattered photons from this emitter. An interesting thing is that if we control the phase properly, we can tune again the statistics. In the first case, if we turn off the coherent source, we will find that the GN are all greater than are all equal to 0 because it's a perfect single photon emitter. But if we use we fix the phase to be in anti-phase with the mean field, we can suppress it, and we will find that the actual fluctuations, as we said, are squeezed, and therefore we find that all the Gn are greater than 1. And if we go beyond that, we can again recover the 2-photon suppression, but in this case the Gn are all different from 0. So because of I think I'm running out of time, I just want to make another example, which is a more complex example. In this case, we are combining both a light field and a matter field, and if they are coupled strong enough, what we are dealing with are the polaritons. So one way to do that is to have a cavity and the same single photon emitter that can be a quantum dot embedded in a cavity. and we have this Hamiltonian in which we have added the coherent pumping. But and yes, of course, because we are dealing with squeeze fluctuations, we expect that the statistics behave in the same way. Something similar occurs with a semiconductor microcavity, and in this case, what we need to add to have this source of squeezing is to have some nonlinear interaction between the excitons. Yeah, okay. Of course, we are dealing with open quantum systems, so we have to take into account the incoherent processes such as the losses from the cavity and the exciton. And in some cases, we need to add some pure dephasing that can be caused, for example, if we buy a phonon bath around the single photon emitter, for example. So analyzing the light coming from these cavities in this kind of systems, what was shown many years ago is that we can find a region where the G2 is less than 1, and this is called blockade effect, and it's coming from the fact that if we put a second photon on the cavity, we have some interaction between them, and then we are precluding the emission of the second photon due to this mismatch between the laser and the quantum states of the system. But if we look at in a more broad picture, what we find is that we can have both this kind of conventional blockade, because we are exciting in branch with the polaritons, but we also can find some regions where we have a much more strong anti-bunching, but they do not correspond to these resonances of the system. And in this case, what we find is what was found by Liu is that this is a completely different blockade. The nature of the blockade is a bit different from the previous case. And okay, just to resume it, to make a little summarize of this, we can separate.
Zubizarreta, just 1 minute.
Okay, so just let me finish this slide, and I will go to the end of the talk. Okay, so the idea is that we can separate this kind of bunching and anti-bunching into the conventional ones, which are just resonances of the system. In this case, the system is dissipative, so we have to diagonalize this Hamiltonian, and we can solve it analytically in this region of having a very weak source, and we can plug these conditions here and find all these lines. And for the unconventional, we recovered this idea from the previous slides, in which we find that these lines are indeed the conditions can be found putting the conditions to create a destructive interference at the one photon level. So in this case, we will find that the G2 is much greater than 1, and in the other case, we find that the blue lines correspond to the 2 photon interference. So okay, I don't have time to describe it in detail, but you can find everything in my yeah, okay, sorry, I want to just to acknowledge the people with whom I work in Wolverhampton and in Spain, and I let you all the references here. The first two are related with this idea of using the coherent fields to change, to modify the statistics of the field. These two ones are related with the measurements of these statistics in the case of the resonant fluorescence, so a simple single photon emitter, and these others are related with the statistics of light in a more general way, in case you want to check them out. So thank you very much, and sorry for my delay.
Thank you, Zubizarreta, for the wonderful talk. From the audience, if there's some question, please unmute yourself and go ahead. Something is unclear.
Hi. Some point which maybe I have missed in the resonance fluorescence case, where you have emission from the two-level system. Why do you find the zero time delay Glauber functions to be non-zero for greater than 2?
Yeah, it's true, but you have to think that what we have in the if we mix the field, both fields, the resonance fluorescence and the coherent field, what we have in the end is not the resonance fluorescence itself anymore. So in that case, we can have a G2 that is non-zero, because
so you are mixing the field coming from the two-level and the coherent state through the Homodyne process, is it?
That's
Okay,
it.
okay. Thank you.
Okay, since we are running quite behind time, let's thank Zubizarreta once again for his wonderful talk.